black body radiation is the light emitted from the surface of hot dense objects as a result of the chaotic motions and interactions of the atoms that make it up. Black body radiation is a continuous color spectrum of light, as shown in the top color spectrum. Below the color spectrum is a power spectrum, which is a graph of the emitted power at each wavelength. The horizontal axis is the wavelength and the vertical axis is the relative intensity. The relative intensity of incoming light is measured at each wavelength and recorded. That data is then plotted, creating a power spectrum. Black body power spectra come to a single peak and then tail off at longer wavelengths, as shown. An ideal black body is an object that absorbs all radiation incident upon it and then re-emits that absorbed energy from its surface as blackbody radiation. In the real universe, hot, dense objects generally approximate ideal blackbodies. These could be stars, planets, moons, cars, coffee cups, etc. If light hits the surface of a block, as shown, some of that light gets reflected. This reflected light is not part of the block's blackbody spectrum. Some of the light is absorbed. Thus, the absorbed energy tends to increase the chaotic motions of the atoms in the block and thus increases the amount of blackbody radiation emitted from its surface. For a darker block, there is less reflected light and more absorbed energy. The greater the amount of absorbed energy, the higher the temperature of the block and the greater the amount of chaotic motions and interactions. A black car sitting out in the sunlight feels a lot warmer than a gray or white car. The increased chaotic motion in the block produces a greater amount of blackbody radiation from its surface. For a lighter block, there is more reflected light and less absorbed energy and thus less emitted blackbody radiation. There are two rules for blackbody radiation. One is known as the Stefan-Boltzmann law. Hotter objects emit more total radiation per unit surface area. The luminosity, or output power, is proportional to the total surface area and proportional to the fourth power of the temperature. So, for an object of a given size, the hotter it is, the more luminous it is. For an object of a given temperature, the larger it is, the more luminous it is. Because the luminosity is proportional to the fourth power of temperature, the luminosity depends very sensitively on temperature. For example, doubling an object's size would double its luminosity. However, doubling the object's temperature increases its luminosity by a factor of 2 to the fourth power, or a factor of 16. Wien's law says that the hotter an object, the higher the average energy of the emitted photons. Since the energy of a photon is inversely proportional to its wavelength, the hotter an object is, the shorter the average photon wavelength. In the visible spectrum, the hottest objects will appear bluer and the cooler objects will appear redder. This runs counter to what is often depicted in popular media. Shown are the blackbody power spectra of an object at different temperatures. The higher the temperature, the more the peak of the curve shifts to the left. The wavelength where this peak is located is used to calculate the surface temperature of that object. How does this work? Shown is a sample blackbody spectrum. The first thing to do is to locate the peak and note at what wavelength the peak occurs. The wavelengths are on the horizontal axis. For this example, the peak occurs at 6,000 angstroms. An angstrom is 10 to the negative 10 meters. Then, by plugging into the Wien's law equation, the surface temperature can be calculated. When the wavelength of the peak is in angstroms, one takes 2.9 times 10 to the 7th power and then divides by that wavelength. The temperature unit will be kelvins. It is important to emphasize that the height of the peak isn't what's important when calculating temperature, only the wavelength where the peak occurs. The heights of the blackbody curves may vary depending on how far away the light source is. However, the location of the peak will not change, regardless of distance. Keep in mind too that the blackbody curve itself is not some kind of big wave, though to some it may look like one. shown in review question 3 are measured black body curves from two different stars. Though the black body curve for star A is clearly higher than that of star B, this could be because star A is either very large or very close to us compared to star B. Since they peak at the same wavelength, at about 10,000 angstroms, they are the same temperature. When comparing stars, the star whose black body curve peaks more to the left has the higher surface temperature, regardless of the relative heights of those curves.